Good afternoon. This is the 47th lecture of AS and A-level chemistry lecture series. And we are talking analytical techniques of the final chapter of the A-level chemistry syllabus. We did talk about gas chromatograph in the last lecture, a detail of gas chromatograph, etc. Today we will discuss nuclear magnetic resonance spectroscopy, that is NMR spectroscopy. Well, the detailed theory of NMR spectroscopy is not needed for A-level chemistry. However, we must have to have a little idea about the theory, but mainly the student will be asked to interpret NMR spectra and deduce the information about the structure of molecules. That what is the content of the syllabus of nuclear magnetic resonance spectroscopy chapter. Okay, this technique is a very powerful analytical technique. And that will, at least in organic chemistry, I would say, organic chemistry, the structure of carbon compounds. That shows the structure of carbon compounds. And we identify unknown organic compounds too. And we can also check for the impurities and also start the shapes of molecules. NMR studies the behavior of the nuclei of atoms in magnetic field. Now I go for explaining this magnetic field. We know that there are spin of different orientation in nucleus. Let us take a proton nucleus. So we could have spin like this, and we could have this spin like this. And then if we apply a magnetic field, we see this one of this spin of nucleus lined up with the magnetic field. Other one is just against the magnetic field. Well, and that's what we will take the advantage of this and then see how we can explain the structure, etc. So this NMR is limited to what sort of limitation we have in this NMR. Nuclei which behave like tiny magnets because they have a property called spin. We did discuss about spin in the atomic structure. Well, that what is then in common organic compounds, we have very many different kinds of nuclei, let's say carbon 12, oxygen 16, nitrogen 14, etc. But we will see that the NMR, the nuclei which has got odd mass number, example, carbon 13, proton, odd mass number, they show on the nuclear spectra. But common nuclei in organic compounds, say let's say carbon 12, oxygen 16, nitrogen 14, they do not show up any NMR spectra. We have to remember this limitation. Okay. When we go for this diagram, and let's say that when we apply this magnetic field, as I say, nuclei line up. So before the applied magnetic field, the nuclei of the nuclei are showing like this spin and that spin, of course. And after the applying nuclear field, after applying the nuclear field, we see that one has with this energy and a little bit higher, which is against the magnetic field energy, has got energy. This difference of energy lights up in the radio wave region. So what we say that here we explain it the opposite direction to it. Those lined up in the same direction are slightly lower in energy. That's what we said. And the difference between two energy levels is known as energy gap. That's what he showed. Well, this is what the main basic principle of nuclear magnetic resonance spectroscopy. So this energy gap corresponds to a particular frequency of radio frequency range. Exactly the right frequency is supplied, a proton in the lower energy level can flip into the higher energy level. And the protons are said to be in resonance. Radio frequency needed for this is recorded in computer and etc. And then we start interpreting the spectrum. Okay, here we are talking about, and then when we say that we will have analyze this sample in NMR spec and get the NMR spectroscopy. So what we do, we take that sample in a tube and dissolved it in a suitable solution, standard solution. Make standard reference solution, dissolve it in it. We come to it later, and we have the tube, the sample, and then we have radio frequency. This is a magnetic field, and it can vary the strength also of the magnetic field. The radio frequency oscillators comes, and then we get radio frequency detector, and with computer, and then decoding it. That is the schematic diagram of a NMR. But this, remember, this is just a schematic diagram. When you see an NMR in real laboratory, you may not see this component. You can see a huge machine with lots of other accessories. Okay. The sample is dissolved in solvent, I said, and the solvent is mostly in proton NMR. We use tetramethyl silane, TMS, and this molecular formula is SiCH3O4. Why you take this standard reference compound? That it produces single sharp absorption peak and well away from the peaks produced by the sample for analysis. Here is a peak for a standard sample, TMS, and this we take as a reference, and this is 0, delta is 0, chemical shift. Okay. Each peak corresponds to one or more magnetic atoms in a particular chemical environment. Do remember that we are talking about chemical environment. Okay, nuclei different parts of molecule experience slightly different magnetic fields in an NMR machine. This is because, why it is? Because they are shielded. Someone is shielded in greater extent, someone is in lesser extent. And this tiny magnetic fields associated with electrons of neighboring atoms, bonded atoms. Okay, we can also have another solvent, and this solvent is CdCl3, a deuterated chloroform or deuterated chloromethane, and that has also sharp general peak, and that we also consider for chemical shift, which is 0. In many cases, I would say many cases, we do not show, we omit the peak of standard sample. Why? We omit the peak of, just for clarity, we omit the peak of standard sample, but we show this, that this is standard peak is always at 0 chemical shift. So that what we missed here, just show the real peak. Why we to make it more clear, we in many books and many spectra, you don't see the standard reference peak, but you do see the zero level of this, zero value of this. Okay, and this chemical shift is measured in parts per million, ppm. We say parts per million. Okay. Now that when we are talking about carbon isotopes, we see that carbon has got an isotope which is carbon-13, equal to carbon-13. And if we compare this with the naturally occurring carbon atoms, we see that isotopes is only 1% of the total carbon. But that 1% is enough for a signal to detect the NMR, detected NMR emissions. Okay, more thing we have to remember that this spectra we get that we can preserve as a database, spectral database system, SDBS, for organic compounds, where it is at the National Institute of Advanced Industrial Science and Technology, NIAIST, Japan. There we have a database, and with this database, we can compare our spectra and using software, and then we can see whether it is a new compound or it is already reported compound. Okay. Next. So here we show the spectra, carbon-13 spectra of ethanol dissolved in CdCl3, which we already said that is the reference one. And you see here we do not have the signal of the reference solvent. We don't have this signal, though it has that signal. And as we said, this for clarity, we just omit the reference signal. Okay. Now you see, this is for ethanol, and you see there are 2 peaks for ethanol. Why there are only 2 peaks? Because if we go to the molecular formula of ethanol, we get CH3, CH2, OH. If you remember, you definitely remember this. We can write the molecular formula of ethanol, which is CH3, CH2, OH. Okay, then this CH3 has got an environment, and this CH2 has got another environment. So different environment gives us different signal. So therefore, we are getting one signal for CH3 and another signal for CH2. Okay. And as I said, SDBS, this is the database from where we are keeping this spectra, removing the zero standard reference spectra for clarification, we said. Okay, that was UCOMT. Now we take an example to see how we interpret the data. Here is a data for 4-methylpentane 2-on, which is dissolved in CdCl3, and that is carbon-13 NMR data. How many peaks we are seeing? 1, 2, 3, 4, 5. If we go to the molecular structure of this compound, we write it like this. This is the molecular formula of the 4-methylpentane 2-on. Then we find out what are we have 1, 2, 3, 4, 5, 6 carbon atom. Is it not? So we should get 6 peak for this. Now we say that it is only 5 peak. Why for that? So we can go to this molecular formula and see the environment of each carbon atom. So if we take this one, it has got an environment, let's say A. What about this one? This must be different environment, must have different environment than that of A. So if we say that's B, then what about this carbon atom? It is different, definitely different environment than that of A and B. So we label it C. What about this one? We can see that this is also different from A, B, C, and therefore we will label it D. What about this one and this one? You see, these 2 carbon atom has got same environment, and therefore, because this 2 has got same environment, we should get 1 signal for it. So here we have different environment 1, 2, 3, 4, and 5 carbon atom. Therefore, we are getting 5 signal for this. Now, I believe we understand what we have to look in the spectrum. In A-level chemistry, we have to interpret, and what we need the molecular formula, and then we look for the carbon atoms difference environment, and then can predict the carbon-13 NMR spectra and see whether we are having a new compound or we are having old compound, and or whether there is any impurities. This is what we can see by this NMR. Okay, now we go for a spectrum. We are saying getting a spectrum like this, and we see it's only one a peak, and it is at 128 ppm. What is that peak? We see that CDCl3 has got a triplet chemical shift at 77.16. We see that we don't have any 77.16 peak here. It has been leveled as 0, and the peak is omitted for clarity. That's what is said also. So what about benzene? If we took the benzene structure, molecular structure, or benzene structure, you see that all carbon atoms are having same environment, equivalent environments. All carbon atoms has got equivalent environments. And as all carbon atoms of the C6 have equivalent environment, so we get one peak there, only one peak. Where is the peak? If we take some other compound and look for that, how we can interpret the spectral data. And if we take a nitrobenzene, for example, nitrobenzene, that is the structure of nitrobenzene. So we find out how many carbon atoms having different environment. You see, this one has got different environment, but this and this has same environment. This and this has same environment. Again, this one has got different environment. So how many peak we should get? 1, 2, 3, and 4. We should get 4 peak. And this is what is the chemical shift of this 4 peak, and intensity also. And that shows that we are having this spectrum is for nitrobenzene. Okay, now we have a summary table for carbon-13 NMR in CDCl3 of compound like benzene, nitrobenzene, ethyl benzene. And we can also see some other spectra and then come back to this one. Already we have explained the benzene ring, you see, all have equivalent carbon, and therefore we get in every position the same signal, 128.4, and there is no side change, so we don't get any peak for that. And here also nitrobenzene, there is no side change, we don't got any peak. We get these are the peak for 4 peaks for this spectrum. And if we take ethyl benzene, we get 4 peak for the benzene ring, and then we have in the benzene ring we have ethyl group, so we have an environment for CH3 and another environment for CH2. Therefore, we have 2 peaks for here, so we should get 6 peak for ethyl benzene. We'll see it later. Okay, here we have to consider another thing, that we do have low resolution NMR spectrometer, I would say, low resolution NMR spectrometer, and we do have high resolution NMR spectrometer. What are the how can I distinguish between low resolution NMR spectroscopy and high resolution LMR spectroscopy? What is that feature? We are talking about peak structure. So low resolution NMR shows only single peak for distinct peaks for each environment, let's say. But in high resolution peak, we say that this single peak splits up into clusters. And there we can see doublets, triplets, quadrets, and then primary use for this low resolution. It's identify number of different types of hydrogen or other nuclear environments. But in high resolution, it determines exact molecular connectivity, functional groups, and neighboring atoms. Okay? And core mechanism is this, that how magnetic environments differ across the molecule. That is what in low resolution we get. But in high resolution, we use the n+1 rule for splitting for peak splitting, and indicates the number of hydrogen on adjacent atom. Let's say we have X atom and the Y atom is the adjacent atom. How many hydrogen are there? We also can see in this high resolution NMR. Why we are talking about low resolution and high resolution? If we take the hardware and compatibility, we see that in low resolution, the magnetic field is lower, less powerful, and the machine is more affordable because of cost effectivity is more affordable. One can have this in almost all laboratory, but in having high resolution NMR spectroscopy, magnetic field is much stronger, higher frequency magnets for superior signal dispersion. So these are the main distinction between high resolution and low resolution NMR. Okay, we take the next one. Well, a low resolution NMR we have been talking about ethanol, and we show what are the environment we have in ethanol, that what we talked about. And we have a table also that says about the chemical shift of different organic compounds and substituted organic compounds. So if we have alkane, so this is the example of alkane, and then we see that chemical shift for alkane is between 0.9 to 1.7 chemical shift delta per ppm. Okay, ppm. Well, what about then alkyl next to carbonyl group? So this alkyl next to carbonyl group has got 2.2 to 3.0 chemical shift ppm. This is a range of chemical shift. Well, I need not to talk about this. You get it in book, and even when you were asked any question giving it spectra, you probably get also the chemical shift in the spectra, and then using this table, or you will be supplied with this table in your exam, and then to identify which peak is for what one, and then you conclude the molecular structure of the spectra you have been given for in the exam. So low resolution, this is, as I said, we should see 3 peaks, one for OH, another for CH2, and another for CH3. You see, this is for OH, 2H, and 3H. Here it is. And so what we do when type of hydrogen atom can be checked against data in table using the NMR to identify unknown compounds. We have data in the table, and then we start looking for the chemical shift of the spectrum, and then we conclude what compound it could be. Okay, here we are taking some more example for you. You see, we are, this is an alkane. This is an alkane, is it not? And the how many peak we should expect for this alkane? How many different chemical environment we look for? That one and that one is the same having same chemical environment, is it not? This one and this one having same chemical environment. This one is having the different chemical environment. So we have A, B, C. We should get in our spectrum a 3 peak. If such a compound alkane is given to us, and the spectrum of saying that here is a spectrum for an alkane, find out how many peaks do you have, and the molecule is such and such, how many peaks do you expect, and in your spectrum. This is the zero reference spectrum, reference line, TMS, trimethylsilane, and the carbon-13 NMR of this. Okay, if we take this one, the propanol, so what you see, that how many different spectra we should expect. This has got a different environment than this one, and this one has got a different environment but from this or this one. So we should have 3 peak. Here we see that 1 peak, 2 peak, 3 peak. And the chemical shift will allow you to say, find out the compound, molecular structure of the compound. If we go for it, this is what we discussed about ethyl benzene, is it not? And we said that we should get 6 peak because we showed it earlier that there are these two carbon atoms, this carbon atom and this carbon atom in the same environment. This one, same. And this one is different, this one is different. So we have 3 and then 4, 5, and for this one, 6. So we have 6 peak. We should have 1, 2, 3, 4, 5, 6. So this is what is the structure of ethyl benzene. Okay. Now we are taking a NMR spectrum, carbon-13 NMR spectrum of propane. You see, this has got, and this one has got same chemical environment. This two has got same chemical environment, and this is a different chemical environment for this carbon atom. So we should have 2 peak. Here is, and here 1. So this is how we analyze the spectrum. This is how we analyze the spectrum. We do remember. Okay. We have to talk about high resolution NMR, but I think then we need a little bit more time, and that would be probably more than 30 minutes. So what we do, we take this lecture, complete it in the next lecture, and also we summarize the series of lecture, the 48th lecture, what are the content of those 48 lecture, and I give a concluding remark of the lecture series for A and AS level chemistry. For today's, we complete here. Thank you very much, and looking forward to having our last lecture, that is the lecture number 48. That is 48th lecture, and that will finish the AS and A level chemistry syllabus. We talk in the next lecture and give the final summary. Thank you very much for your attention. Thank you.